start recording.
Yes, so hi everyone. Thank you for inviting me, and thank you, Pau, for organizing this. I just looked at the list of speakers, and I have to say you have some very good choice of topics there and very good speakers. So I think people here will enjoy a lot this event. So it's a good initiative, Pau, and thank you for that. And it's a pleasure to open it. It's also some sort of a responsibility. So as we said at the beginning, the whole point is that you ask questions and interrupt me. I have much more than I can fit in 45 minutes or even 1 hour. So I'll just pick and choose as I go, really, depending on what people are interested in, depending on where I see the wind is blowing. So the thing I will tell you about, the story I will tell you about is about this picture really that we're looking at, and I hope we are looking at. Mm-hmm. So the title is The Two-Body Problem, General Relativity, the Cell-Force Approach. Is a bit of a mouthful. It's you could replace the title with the title How Things Move Around Black Holes. So this is what I'm going to tell you about. How, if I have a small thing that is in orbit around a black hole, how do I describe its orbit? And later on, we'll talk about how we describe the gravitational waves that this emits. So in one way, this is a small problem. Yeah, it's a very specific physical system, and there's a very specific question here. So it's not as big as some of the other talks you will be listening to in this a workshop, like cosmology, big questions, but in some other ways it is a big topic. So for one, there's a sizable community of people from different disciplines who are looking at this for a long time now, about 2 decades. I'm talking dozens of people, and so sort of this problem is sort of a meeting point for people from astrophysics who learn about formation mechanisms of systems like that in astrophysics, and people who study the mathematics of GR, who are interested in understanding how things move in curved space-time, and this kind of problem sits at the basic of this kind of system. And then there are people who are interested in high energy physics and want to learn about how the observation of such systems and gravitational waves can teach us about what gravity does in its most extreme regime, and whether we can learn about possibly deviation from Einstein's relativity by observing those things. And then there are people who are doing the gravitational wave experiments, and they are interested in these systems from the point of, they're interested in all the nitty-gritty of the data analysis, and it's a very, very hard and interesting and complicated problem from the data processing point of view, because those signals are extremely complicated. And so you have these conferences where all of these people sit together, coming from very different places, and try to talk to each other. That makes the entire endeavor very, very interesting. So, here, what I set out for myself to do is summarize here in this plan, or rather a menu, because we are going to choose and pick from this, depending on how much time and interest there are. So basically, this is, let's see if I can get this to work. Yeah, good. This is a review of the effort and it's an ongoing effort, it's been going for about 2 decades now, to model the dynamics of black hole binaries in the regime where the mass ratio is small, and then predict the gravitational wave signature. So I'll start by putting things in context, so both physical and astrophysical context. I'll tell you about the motivation. So the physical context is a two-body problem in GR, and I'll specialize that to the large mass ratio later. And then the astrophysical motivation would come from those things that we call EMRIs, extreme mass ratio inspirals, which are one of the key sources for LISA. And I assume that you've heard about that. It's a detector that we are planning to put in space in just over a decade from now. Let's see if that works. So launch 2034. And it's a triangular array of satellites, a bit like a big LIGO in space, but where the base here is a few million kilometers, that's set in an orbit around the sun. and then each of these, these three satellites exchange laser rays between themselves, and by measuring the variation in distances between the satellites, we detect gravitational waves.
Leor,
Yeah.
What is an MRI? I'm not following.
Yes. We'll talk about this a lot in the next.
Okay.
Extreme mass ratio in spiral.
And why is it important to do this in space if we are doing this already in the ground?
Yeah, I'll explain that in the next slide.
Okay.
Thank you. Okay, so that would be the first part. The second part, I'll take a few or many steps back and talk about the mathematical foundation of the problem and how we model those things by solving the relevant field equations in curved spacetime. Tell you about this a little. Perhaps I will just touch briefly upon how we convert this mathematics into actual computation, and then I'll just flash a few results at you at the end, show you what people are working on now, and sort of mark all the open problems and interesting things that the students among you may perhaps want to look at for projects. So yeah, so let's learn how to use this system. Well, there you go. Yeah, so I'll talk about MRIs and the astrophysics in a moment, but I thought I should start by, since the underlying physics is a two-body problem, let me just remind how it works in Newton theory, and then I'll do a very rough comparison with GR, just to explain why it's hard, all right? So, yeah, so two-body problem. It's most basic, non-trivial problem in gravity, in gravitational physics. And when you do Newton, the situation is pretty simple. We have these two masses, M1 and M2, and they are in some interaction with each other, and there's nothing else in the universe, there's just those two things. And one thing that helps a lot in the Newton problem is that you can, in many situations of interest, just reduce the problem to that of point particles. And point particles make perfect sense in a Keplerian, in a Newtonian framework, because the equations of the theory are linear. And so you can just think that you have two delta functions, and you can solve the relevant equation exactly with delta function masses, so masses that are concentrated on delta function. And when you do that, the problem is really very simple. So let me just write that we are doing a point particle reduction. Point particle reduction. And by the way, point particle reduction does almost the entire thing for you in many cases. So the solar system, you can consider a point sun and point planets, and you'll get the orbital motion very, very accurately. And even if you're interested in things beyond that, so when you take into account the internal structure on things and the internal dynamics, the dynamics coupled to the orbital dynamics via tidal forces, for example, and you can get this kind of more subtle effects. But even if you're interested in these more subtle effects, then still point particle reduction provides you with a good zeroth order approximation upon which you can base some sort of a perturbation scheme, and you can include the correction order by order in some small parameter. And that makes perfect sense in Newton theory. So if you have point particles, then solutions are very simple. These are the conical section that you're familiar with, I suppose. So simple solutions, conical sections. So you have those exact ellipses and hyperbolas, and you have bound orbits in particular, and bound orbits are also closed. So you get exactly closed ellipses and nothing else. This is extremely simple. In GR, the situation is nothing like that. So first of all, you can't really reduce the problem to point particles in any exact way. You don't have point particles in GR. The equations of GR, the Einstein's field equations, are not consistent with point particle sources. If you try to squeeze a mass into a point, you'll get a black hole before you before you get a delta function, right? So no point particles in GR, strictly speaking. And the fact that you can't even in principle talk about point particles complicates things a lot. So as we'll see in a moment, you can sort of effectively talk about point particles, but just to make a concrete mathematical sense of that requires a lot of effort and requires many decades of development in mathematical GR to get to. And so the simplest object in GR, really, a compact object in GR is not a point particle, but a black hole, really. So let's talk about black holes from now on. Simplest object is really a black hole. And famously, it is said about black holes that they are the simplest macroscopic objects in the universe. Here's a black hole. It is very simple, so it's happy. The simplest, as Chandrasekhar said that in his book, simplest macroscopical object in the universe. You know, all black holes, if they're in a complete isolation and nothing else exists around, they are precisely Kerr, and they are all the same up to two numbers: the mass and the rate of spin. They're all the same and described by a simple gravitational field. It's a remarkable result of general relativity. And I'm saying this because I want to contrast it with the case where you have two black holes, which then immediately turns the problem into extremely complicated. Just add one more, and you completely lose track of the physics in general. So that's the case that we are interested in here. We have two black holes going on each other in orbit. The problem becomes extremely complicated. And why is it so? Well, first of all, beyond the issue of it's hard to make an effective picture of point particles without some effort. There is the non-linearity, a famous non-linearity of the field equations. Non-linearity, which means that the gravitational field of the system of the two black holes is not just the sum of the two gravitational fields of the individual black holes.
Wait, Leor, is everybody following? Because Leor has said a couple of things, and I'm not so sure that everybody is aware of that. You said something about Kerr.
The non-linearity, I can talk more about this.
No, you said something about Kerr. You talked about the spin.
Okay.
People, come on, speak. It's not that. Come on, I know that some of you know, but about Rainer, Miguel.
So my assumption is that people heard about gravitational waves and LIGO and black holes at a very basic level, and the Kerr solution, know what a metric is. But if this is not the case, I'm happy to go one step.
Yes, but you made some statements, and I'm not sure that come on, Joel. So Leor said these are the simplest microscopic objects in the universe. Don't you have any kind of questions? Leor is here exactly for that. No comments? Zero?
Yeah, let me say a few words about that. When we look at the stars can come in all kinds of shapes and forms, and they are complicated. The gravitational field of a star depends on what the star is made of, and there's very complicated physics going on in the star to do with magnetic fields, for example, can cause deformations, and deformations affect gravitational field, and so on. It's a mess, total mess. And when you have a black hole, it's very, very simple. The solution is always the same.
Sorry, Leor. Here I'm getting this kind of message. Instek would like to speak. If you would like to speak, speak simply.
Yes.
Salon Instek.
Hi, can you hear me?
Yes.
Okay, I have a question. When you are going to solve the impact between two compact bodies in its dimensional impact in space, why do you prefer to solve this problem using Newton-Kepler equation or GR?
I couldn't hear you very well because of some echo. Pau, did you hear that?
I also had some trouble. Okay, can you get closer to the microphone and
Yeah.
repeat it slowly? Now you're muted completely.
Yes.
Lento.
What I say is, what do you prefer to solve the problem of the impact of two compact objects in dimensional space using Newtonian equations or ER rather than momentum or energy conservation law? I mean, I remember when I was working on a project, when I was a freshman, we were trying to solve the problem of the impact between two three-dimensional objects. But when you are using the momentum equation law, you are going to have three different equations, maybe the three different components in space of the momentum. Okay, you know the initial condition. But moreover, if you use the energy conservation law, you are going to have four equations total. But you are going to have six unknown variables. I mean the three final momentum for each component of two bodies. So how you resolve this problem? You have four equations to solve this problem and six variables. But I don't know how can you resolve this. We apply a fast method, a particular method, but how can you approach this problem?
I think you're jumping forward.
Forward and backward at the same time. So you are, if I understand correctly, you're asking about the possibility of solving for this system in GR using conservation laws, right? Conservation of momentum and energy. But I wanted to say, I want to take you a step backwards and say that to apply these kind of methods, you need to have point particles to begin with, and we don't have those in relativity. So that's just to make sense of a picture where you have point particles requires a lot of effort, and I'm going to tell you about that in the next few slides. And second, to formulate conservation laws in NGR is a complicated matter. Complicated business. You don't have conservation, strictly speaking, of energy and angular momentum, except when you have very high degree of symmetry. And even then, it's a very delicate notion. It's not at all like in Newtonian physics. So I wanted to take it from a bit more basic point of view and develop it from there, and we'll get to those notions later on in the discussion. What you were discussing, I suppose, is maybe a geodesic motion around a black hole, where you can identify constants of motion, energy, and momentum. Yes, we'll talk about this later on. But for now, we don't have this. We have two black holes, not point particle, two black holes, and they are in orbit. And you have to solve the full nonlinear Einstein equations. And you don't have conserved energy anywhere in the system, really, or momentum. You don't have those things defined, and nothing is conserved. Okay, so if you wait, we'll get back to those issues later on. Thank you for the question. Okay, so where was I? Yeah, I was still explaining describing the differences. So one was the nonlinearity. So the equations, the Einstein equations, are very nonlinear, which means that you can't just construct the field as a sum of two black hole solutions. You know, in Newton theory, if you want the gravitational field here, you just add the field of this mass to the field of this mass, you do superposition, and you get the full solution. That doesn't work in GR because the equations are nonlinear. That's one difference. Another striking difference is you don't have bound states at all. No bound orbits or states. If you start with a universe in which you have two compact objects or black holes, and you let it evolve in time, there are only two end states. One is a single black hole, And another is a universe where you have a separate black hole flying out into infinity. And there are no other states. You can't produce a bound system. You can't produce a solar system. Right? It's a striking difference. Only two outcomes, either a big black hole at the end or a lot of black holes, or two black holes flying out to infinity. And nothing else. There's no bound states. And the reason is, of course, that you have gravitational radiation. The interaction between the two objects emits gravitational waves. There is exchange of orbital energy to the energy of gravitational waves that are emitted and fly out to infinity. And so if you start on something that looks like bound, let's say a circular orbit, over time the system will lose energy and inspiral and then merge and become a big black hole in the center. So all you have to do is wait enough time, and you'll get a single black hole in the end. And then there are all kind of small details. Maybe I should skip, but we don't have precession in Newton theory, not with point particles, but you do have precession in relativity. So orbits are not closed, and you have precession of the periastron as well as precession of the orbital plane. So as I'll show you in the pictures in the next two slides, the orbits can look very complicated. Let me push on. I want to show you a map of the two-body problem in general relativity. And on this map, I'm showing the different methods that people are using to solve the equation that describes the motion of two compact objects, specifically black holes. So the two relevant directions in this parameter space of binaries are the mass ratio on the horizontal and the distance between the objects, separation, at a given moment. So let me show you what we are looking at picture by picture. In this corner here, when the mass ratio is not too disparate, too different, it's close to 1, the two objects have a similar mass, and they're also close together, it's very hard to do any approximations. So the person who asked the question later would suggest that there might be some conserved energy, but there isn't any identifiable conserved energy for a system like that, or angular momentum. The system is very nonlinear and changes very quickly. And as I said, it's hard to do an approximation, analytical or otherwise. And so what people do is put that on a computer, a big computer. You need a very big computer for that. And then solve the equations, the ancient equations, numerically on a computer. And that is a very hard thing to do. And people have been really trying to do this since the 1970s, since really people started to use computing in physics, only to succeed 2005. So it took 35 years to actually manage to run a simulation that shows how space-time evolves when two black holes merge with each other. So you have this nice picture of two throats that merge into one black hole. So that's the kind of simulations that feed into gravitational wave experiments like LIGO nowadays, because you need these predictions of the waveforms, the gravitational waves, in order to extract the signals from the output of the experiment. Now, the nice thing is that as you move out of this troublesome corner into either direction, you pick up a small parameter that allows you to build an approximation scheme and in particular, identify the conserved energy and so on, and do an approximation. So if you move up in the separation, and this is in fact what systems like that start in this corner of the parameter space. They start far apart, and then they inspiral and with time enter the numerical relativity regime. But before they do so, they live in a region where they are far apart. And then you can build an approximation based on an expansion in the distance between them. Or, essentially equivalently, in the velocities. The velocities are going to be quite small. And this is called a post-Newtonian approximation. So what you do is think of it as a kind of a Newtonian system at leading order, Newtonian forces, but then you have small corrections that come from the gravitational interaction in GR. So you sort of expand the equations of GR in the small velocity of the system, and you solve it order by order in the small velocity. This is only possible if the velocity is small enough. But these methods have been extremely successful, and they can be used to model a large variety of astrophysical systems, like the binary pulsar, for example. So many systems where the two objects are not too close together, that's perfectly sufficient to model them using post-Newtonian methods. Another type of sort of weak field approximation is a post-Minkowskian technique, in which you expand not by the distance or in the distance or velocity, but by this gravitational constant g. So you can solve for a situation where the velocity can be very high, but the distance is still very large, so the interaction is small. You expand, you solve the Einstein equations order by order in g, the gravitational constant. So, for example, the two black holes scatter out of each other in a hyperbolic orbit, not getting too close to each other. That would be a good approximation to use. Now, what I mostly want to talk about is this corner of the parameter space, where you have another small parameter, and that's the mass ratio. Okay, so as I move here, we're looking at systems where one of the objects is much larger than the other. And here again, you can do an approximation method, this time based on an expansion in the small mass ratio. And this is our territory, the territory of black hole perturbation theory, or what we cell force. What you do here is at zeroth order, you just have one black hole, and you know what the geometry is a Schwarzschild geometry, or the Kerr geometry if it's rotating, that people learn about in first course in relativity. And then you have a small object next to it, and at leading order, as we shall see, it's just moving on a geodesic of that spacetime. Geodesic is a sort of a shortest distance trajectory around the black hole. And that's at leading order, and there's no interaction between these two things. The little thing does not affect the spacetime at leading order. It's like a test particle. At next order, you take into account corrections that are linear in the mass ratio. And then what happens is that this little thing is going to experience a sort of acceleration that comes from its own gravitational field. So it's as if there was force that this little object exerts on itself, because it's moving in the gravitational field of itself. And that pushes it away from its geodesic motion. And you can take these effects into account order by order in the small mass ratio. If these things have a structure, some tidal moments or spin, then you can also take them into account order by order in the small mass ratio. So that's the territory we're working on in when we look at MRIs. We're going to talk about MRIs now. Anyone has questions on that diagram, please?
Diana, come on, you don't have to ask for permission, just talk.
Approximately, what is the lower mass ratio from which perturbation theory can be used?
Very good question. Yes, we don't know. But at the very end of this lecture, of this talk, I will show you a graph that suggests what that may be. So this is a sort of fuzzy borderline. We expect there to be some sort of a transition, but what the transition is exactly, that's a question that people are looking into, really. It's a very important question. And the same applies, by the way, when you look at the other interfaces here. What we're hoping is that if you put all of this together, there are no gaps left in this parameter space, and you can sort of get a universal model of the two-body object, combining those things together.
And Leo, why don't you just put these equations into a computer and solve them?
Say again?
Why don't you just put these equations for the large mass ratio into a supercomputer and solve them? Like you do with a similar mass ratio.
Good. Thank you for asking, because I was meaning to talk about this, but I forgot. Yes. Why can't you just do everything with numerical relativity? Good question. So numerical relativity has a problem to get into here or into here. And the problem comes precisely from the fact that you have a large scale disparity. The number of orbits that this object undergoes before it inspires is proportional to the mass ratio, to the large mass ratio. So if the large mass ratio is a million, as in some astrophysical objects that we are hoping to observe, you'll get a million orbits here. So it's nothing at all like the LIGO orbits when you get a few orbits and slam. You get a million of them. And numerical relativity can't run for that long. This, even to run it for, let's say, 10 orbits, typically take weeks to months on a supercomputer. To run to a million orbits is completely intractable. That's part of the problem. Another part is that you need to resolve the small scales of the problem. And again, that's computationally very expensive. So numerical relativity really can't penetrate very much into this regime. We have accurate simulations going to 1 on 10 today. There's one illustration of 1 on 100, but a very short one. So it's not satisfactory at all. But there is a very fundamental computational barrier that forbids you from crossing too deeply into this region. The same here, by the way. If you want to start very far apart, there will be a large computational cost that will make it prohibitive. So what they do in simulations for LIGO, they do an analytical approximation, and then they patch it or they fit it into a numerical simulation later on when the two objects are closer together.
Costa, do you want to ask something? I thought I saw you raising your hand.
Yes. Perturbation theory, how well defined is it in the context of relativity?
Yes, so what I'm planning to show is that it is mathematically rigorous. I mean, you can do it in a mathematically rigorous way. A set of, you use nothing but the Einstein field equations without any further assumption, besides global conservation of energy, perhaps. And you can write down equation of motions that describe the motion of this particle in an entirely mathematically rigorous way, using something that's called matched asymptotic expansions that I'm hoping to talk about in a few minutes.
Okay.
Okay, let's move on. And finally, I'm getting to the motivation for looking at the small mass ratio.
Leor?
Yeah.
Just a quick question. I really like this picture of thinking of GR in terms of this wells, and I just wanted to cross-check all these throws, as you call them. They have grounds, except we go for the point particle limit, right?
So, sorry, ask again. They have these throws here.
Yeah. So they have a base at some point. They don't go to minus infinity. Like they are not infinitely deep, right?
No, I want to cut them at the event horizon here.
Yes.
Yes. Mm-hmm.
Okay.
Yeah. No. So in numerical relativity, there are different ways of dealing with what's inside the black hole. There's excision, where you remove everything that's inside the black hole and you replace it with some boundary conditions. And there's a puncture method where you approximate the singularity with some analytical function and also effectively take it out of your numerical domain. All kind of complications that go with having to deal with this kind of singularity in the center. But yeah, it's not the topic of this discussion. There are no point particles. The singularity in the black hole is not a point particle, not at all. It's a space-like surface that is the future boundary of the interior. It's nothing like a point singularity.
No, but yeah, I was just trying to connect. In the Newtonian picture, you would just have this infinitely deep point particle.
It's not a point particle. The singularity in Schwarzschild
No, I'm talking about the Newtonian case.
Yeah.
Where you would think in terms of
yes. Yeah, you will have this
point particles.
That's right. No, here you have an event horizon where you cut your simulation and you need to do something there in terms of boundary conditions. Yeah,
yes.
Absolutely. That's a good question. Okay, let's move on. And I'm going to talk about some astrophysics. So this is Pau's territory now.
Okay, let me go back then.
Okay, we're going very far.
What do you mean that the particle is interacting with itself? I know.
Yes.
I mean, I know what you mean, but I am sure that a couple of people did not.
Yeah,
They're not asking.
Yeah, so this is a nonlinear theory. This particle is a source. It has a mass, so it is a source in the Einstein equation, and it produces a field, perturbation of the background geometry, right? So if you take that into account, then this is the total field is not only a Schwarzschild black hole, but a Schwarzschild plus some small field that comes from the particle, from the small object. It's a small black hole, not a particle. Now, this small object is now moving in a combined geometry that is not exactly Schwarzschild, but Schwarzschild plus perturbation. And there's a back reaction from that perturbation on the motion of the object, as if it exerts a force on itself. That's one way to look at that. So I'm going to formulate this in about 3 slides below in a more precise way. But one useful way to look at this is to say that this thing is okay. I need to tell you much more in order to make precise what I was about to say now.
But could you make an analogy?
The physical picture is that you have a self field that this object produces, and that self field exerts a force back on the thing that produces it. You have the same thing in electrodynamics. Yes, you're familiar with the Abram-Lorentz force or Abram-Lorentz-Dirac force. Accelerated particles electrons in electrodynamics experience a self force, which is a force that's proportional to the square of the charge, the electric charge.
Okay.
It comes from back reaction of the field on the motion. Okay. So astrophysics, yeah. So why are we so interested in this kind of extreme mass ratio? So here's the acronym that I had before, EMRIS, extreme mass ratio inspals. And since a while ago, we know, people have realized in the 90s that the universe abounds with things like that may be detectable with a gravitational detector put in space. So we are looking at systems where compact objects, including stellar mass black holes or neutron stars, go around big black holes, inspiral into big black holes, and eventually fall into them. So the big black holes I'm talking about are the massive black holes that live in the center of the galaxy. So here's a picture of a Milky Way. And we know at the center there's a very large black hole. On solar scale, it's very large, about 4 million solar masses. Here it is represented by this black dot. And we know that statistically there's a chance of a small object like a stellar black hole from the cluster in the of stellar objects around the center of the galaxy to be scattered into a tight orbit around it. And if the parameters are right, so most of the time the scatter will end with nothing. Either the object will fall into the black hole or get scattered onto the other side of the galaxy. But there is a small window in the parameter space where particles lose a little bit of energy. They pass very close to the big black hole, lose a bit of energy, and such that the orbit shrinks a little bit in a way that they come back again, only to lose a bit more of energy, and then again a bit more. And every time they do so, the orbit shrinks a little, and fast forward a million years or so, you end up with a very tight orbit around the black hole, going faster and faster until you plunge into the big black hole. And these are those EMRIs that we want to observe. Now, because the big black hole has a mass of millions, the frequency that is emitted won't be in the kilohertz like it is for LIGO sources, for small black holes. It will be in the millihertz, about 1 million times larger wavelengths, smaller frequencies, millihertz. And those things are not observed from Earth with LIGO. LIGO is a small detector of arm length of 1,000 kilometers. It can measure kilohertz frequencies. To measure the really low frequencies, you need much larger arm length, and for this you need to go to space. And so that's when people started to think about detector in space to measure millihertz frequency gravitational waves, and people came up with LISA. LISA will see those supermassive black holes either two of those big ones merging into each other or small object falling into a big black hole. So that's a natural place in the universe where you get those MRIs. And so as I wrote here, LISA will be sensitive to central massive black holes that have masses in the range of, say, 1 million to 10 million solar masses. So the mass ratios we're looking at it can be very small. So we are in the realm of black hole perturbation theory. In our own galaxy, these events may happen, I don't know, once in 1 million years, perhaps. The rays are very unclear yet. But these things will be visible to very great distances, in fact, cosmological distances, that of maybe 1 or 2, even more for the brightest of those sources. So if you integrate over all the galaxies that you can see, you end up with very nice numbers, very large error boundaries. We still don't know how many LISA will see, but it may well be in the hundreds or thousands. And the main thing to consider in terms of the physics is the fact that you have two disparate timescales in the problem. One is the orbital timescale when it is in the LISA band, so when it's very tight around the big black hole, which is of order hours, and it is much smaller than the radiation reaction timescale, so the timescale for the orbit to change due to emission of gravitational waves, which is smaller by a whole small mass ratio, so it comes out to years. So you have something that moves almost without being affected by radiation reaction very many times because of that. But over the scale of maybe a year, it will shrink gradually and eventually fall into the black hole. And LISA will be there to observe for a few years, so we will see the entire process. So that drives sort of the physics that's underlying those things. You have something that changes slowly over many, many orbits and eventually plunge.
Leor?
Yeah.
Can I ask you a question?
Sure.
Yeah, so if I understand this properly, can you also, observe like towards the galactic center also sources with LISA, because you can still have this extreme mass ratio and spirals within our galaxy, right? With respect to Sagittarius A star. Is this possible?
Yeah, if we have one of those in our galaxy, we will see it. It will be extremely bright. The question is that of rates, and Pau is an expert on that. We don't know how many of them per galaxy we might expect to see. And
I was only curious because I've always heard in talks also from Pau and some other people where they talk about the zone near the galactic center where you can have a lot of black holes and we just don't know. So maybe I'm doing a bad job.
That's precisely the status of things. We simply don't know.
Yeah.
But there are scenarios where you might, I think Pau may be able to comment, but you might actually be able to see a type of objects, brown stars, brown dwarf, I suppose, Pau?
Don't believe anything I say, Basu.
Okay. There's a big unknown there.
Okay. Thank you.
The point is that Leor is so we think that one of these things should happen. So one of these extreme mass spirals for a stellar mass black hole should happen every 100,000 years. Taking into account that at least it's going to last, say, 5 years. You divide 5 by 100,000, you get a very small probability, right?
Right.
But so you will be very lucky to catch one of them exactly at the galactic center when LISA is launched and lasts for 5 years. But there are other objects, probably like brown dwarfs, which probably will be there, and the Newtonian stretch is going to be huge. But I will not say anything else.
Okay, thank you.
I also have a little question, if you can hear me.
Sure.
If we increase the arm length and look at lower frequency waves, I'm wondering if that actually helps or hinders the kind of detectability. So when the wave is slower, then there's longer time in which this kind of force can act, caused by this deformation of space-time, can act on the mirrors, for example, and displace them. Does it mean that we can see lesser amplitudes, or is there also a scaling with omega that kind of makes it maybe even harder?
It's a very good question, and I need to think about it to give you a good answer. So there are different. Yes, you gain and you lose in different areas. So of course you see bigger black holes, more MRIs, larger mass ratios, so more orbits. But I'd imagine it's harder to to do the time delay interferometry that you need to do to produce a measurable signal. The longer your arm length is, your laser will need to be stronger. All kind of sources of noise will be larger, like photons. Noise that comes from photon statistics will be larger when your arm length is longer. So it's a a question of both technology of science.
There is probably another reason for that, and it's the following: if, from an astrophysical point of view, things work, the way we think they do, and this is probably one of the one of the fields in astrophysics which I trust the most, because we seem to be able to reproduce things with observations. If you move towards the left, so towards lower frequencies, you're talking about 10 to the 7, 10 to the 8, 10 to the 9 solar mass black holes, right? And those black holes will very likely not have that, say, cloud of compact objects around them, because they have not had enough time to, as we say, and they use in jargon, relax around them. So it's going to be very unlikely that you get one of them.
Yeah. In the meantime, another point I think is that it gets harder and harder to control residual forces on the test masses in lower and lower frequencies, and that you would need to. So I'm looking at, so there are more sources, stronger sources of noise as you go to lower frequencies that come from things like solar wind and solar radiation. These are very low frequency, and it becomes worse and worse with the lower frequency. So expect there to be great technological difficulties.
Right. Okay.
Yeah, that's a bit beyond. Okay, so yeah, so why are we so excited about those things that so many people spend so much of their time trying to model them? Well, in one sentence, we think they are the best system or natural experiment that nature gave us with which to understand or to study strong gravity. And I don't think there can, even in principle, be any better system than that. It's like your natural probe of gravity. So to understand that, let's look at how an MRI orbit looks like. So here's a picture of an actual geodesic orbit that I've drawn here is just a segment of a geodesic, without even taking into account complications from radiation or back reaction. And when you just look at radiation, you can appreciate how complicated the orbit is, contrast it with Newton. So the orbit has 3 periods. So you have one rotational period, so the ordinary motion in the phi direction around the big black hole, and 2 libration type motions. So one is the motion on the ellipse, sort of motion from a large radius to a small radius. When we move on an ellipse, that's what you do, go periodically from a large orbit to a small radius. But because the ellipse itself keeps going round, it gives you this more uniform shape around the big black hole. And so that's one libration motion, but there's also a libration motion in the vertical direction. So in GR orbits, if the central black hole has spin, orbits are not going to be planar anymore. There isn't conservation of orbital angular momentum. There's still a conservation of total angular momentum, but that total includes the spin of the spacetime itself in GR. The spacetime itself has spin that comes from the big black hole. And it's such that the orbital angular momentum does a sort of precession around the direction of the spin. So if you have an angular momentum in one direction, it's going to just go around the direction of the spin angular momentum. And so in effect, you get another libration type motion where the particle goes up and down in theta, in the theta direction. And you combine the two things, you get this complicated thing that fills in the interior of a torus. And so the orbit is ergodic. Ergodic means that every point in the space inside the torus will get visited at some point, if you don't have the inspiral and radiation. So it's this kind of space-filling motion. Now, if you look over radiation reaction time scale, it's much longer than the segment of the geodesic that I've done here. Then also the principal elements drift in time, namely the radius change in time, the eccentricity change in time due to radiation. But also the phases of the ellipse drift in time, and that changes the rate of precession. And this all leads to a very complicated kind of motion. And I'm going to play a movie to you that shows you how these things actually evolve in time. Okay, so let me unshare this screen so I can show you another screen. And then I'll explain to you what we're looking at. Let's see if I manage this.
Yeah, and then meanwhile, Diana, you wanted to ask something. Go ahead.
Yes, before I go.
Okay, what consists the back reaction?
The emission of radiation. So I mentioned one way to look at back reaction is the small object interacting with its own gravitational field. Another way to look at it, or look at the same thing, is to say that there is an emission of gravitational waves, and so orbital energy is being deposited into the gravitational field that gets radiated away and carries away the energy from the orbit. So the orbit starts shrinking. That's what I mean by back reaction from radiation.
Okay, thank you.
And that also causes the eccentricity to change over time. So let's see if I can manage this feat of engineering, which is to share another screen. So how do I unshare? Stop sharing. Stop sharing. Yeah. Am I still sharing?
Yeah.
Yeah. Okay, I want to share another screen. Let's see. Share your screen. Allow. That's me now. Hello.
Yeah.
Maybe this one. Yes. Okay. Do you see this box with two black dots in the middle? How do you see my screen share with the box?
Yes.
Very good. So the shiny black hole. So the shiny black hole in the middle is the big black hole, and the little dot is the small object. This simulation has a big black hole of 3 million solar masses in the center, and the small object has 270 solar masses. So this is all real time and real dimensions. This is a bit hidden, but the scale on each side is about 1 astronomical unit. So it's the size of the orbit of the Earth around the Sun, so to give you an idea. That's roughly the size of the orbit. And you'll see the little one start moving around the big one, and the orbit will change over time. So what was done in this simulation, which my colleague Steve Drasko prepared many years ago, is to use approximate methods that account for the back reaction force, or the emission of radiation. They are approximate, they are based on post-Newtonian approximations. They're not precise, but they give you a qualitative idea of the kind of motion that you'll see. And the idea is to impress you with the complexity of it all. So I'm going to play it now, and I'm also going to play the audio. So I'm translating the gravitational waves emitted into sound waves. But because this is very low frequency, this is millihertz, you won't be hearing them unless I bump up the frequency, and I do so by a factor of 1,000,000. So I'm shifting them to kilohertz. That's audible, and you'll be able to hear the gravitational waves. So here is how an MRI looks and sounds like. At the bottom, you will see one of the polarizations of the gravitational waves as it reaches the Earth. And you'll see, of course, as I said, the motion is not planar. The central object is spinning. The frequency is increasing. And you see the scale is also shrinking. So we are zooming into the big black hole because the orbit is shrinking. The speed here, I think it's a bit out of the window, but the speed is about a third the speed of light. So let's just stop to appreciate that. We are looking here at a black hole that has 270 solar masses moving at 1/3 the speed of light around the big black hole. You can't get much more extreme than that. And the orbit is right outside the event horizon. I mentioned that there are 3 vibration frequencies. They can resonate with each other, and you get interesting resonant patterns. You may have noticed that, and you can see a bit of that here. And that's it. And that's an memory. And the end bit is what tells you that you're looking at a black hole. The signal just disappears abruptly at the end. Okay, if you didn't have a black hole, it wouldn't disappear like that. So we show these movies because we want to impress people with how complicated the signal is. Can you still hear me, by the way?
Yes, we can hear you, but the image is froze.
Go back to my
back.
slide.
So here, every image was 1 day, right? If I understood this.
Yes, the length of a track was 1 day. Yeah, this was the resolution.
I have a question on this simulation. You said that this was done using the post-Newtonian approximation, right?
Yes.
But is it valid when the speed of the smaller black hole is 1/3 of the speed of light?
No, absolutely not. That's a good point. Yes. So there's a bit of cheating here. We're using post-Newtonian formulas, pushing them to a domain where we don't expect them to be applicable. What we do expect them to give us is a sort of qualitative picture. You see the shrinkage, all the frequencies of the problem are there, and qualitatively the features are there. So, and I think it is to the extent that if I looked at that and I looked at an actual physical memory, I wouldn't be able to tell the difference by eye. But of course, the gravitational waves that you will get from this will be very different than what you'll get from a real memory. And we need to know what it is in real, not what this artificial model gives you. So
could we get a better results if we include higher order terms, or would just perturbation theory break down?
So post-Newtonian theory breaks down. We have 4. We know a certain amount of post-Newtonian terms, 4 post-Newtonian terms in the dynamics. This is not sufficient, not at all sufficient. And to go to the next order in post-Newtonian theory, it takes many years of work. So it's not a practical approach. You need black hole perturbation theory and, as I described, an expansion about the geometry of the big black hole in the center. And in a moment, I'll tell you how high an order you need to go in that expansion.
What I actually meant was that in certain systems, like for example the quadratic anharmonic oscillator, the perturbation theories just doesn't work. So could it be possible that you end up in a similar situation with perturbation theory here?
It doesn't work because of resonances?
No, the series diverge. In perturbation theories, you might have series that diverge. So
I see.
Could it be possible that we end up in a similar situation using perturbation theory for?
Yes. So of course the hope is that if the parameter is small enough, it will not diverge but converge, and we have strong numerical indication to show that this is indeed the case. And indeed, things I won't have time to show here today is that we have indication that perturbation theory works in a way even when the mass ratio is 1 and it converges and not diverges. So we don't know mathematically the answer to that, but we have a numerical indication to suggest that in this case it works. We know in post-Newtonian theory, for example, that perturbation theory does not actually converge, mathematically speaking, but it is an asymptotic series, and in a certain domain it gets better the more terms you add to it. It is a good question, yes. We'll never know because we won't be able to calculate more than the first or the second terms in the series. So yes.
Sorry, yes. Well, you say here over orbital time scale, the orbit is ergodic in general. What do you mean with that? So is it always space filling, or is it sometimes, or
you know the answer, right? Yeah. So when the orbit hits a resonance, I mentioned that there are two frequencies: one radial, going out and in and out, and another longitudinal, going up and down. When the two things are in an integer ratio, then they resonate, and then the dynamics changes a lot. And then for that short period of time, the orbit becomes not ergodic. The phase sort of freezes, and you get a pattern that is not ergodic. So resonant orbits are not ergodic. If you go to the review paper I wrote a couple of years ago, there are some nice pictures there I put of non-ergodic resonant orbits like these.
And those resonances, are they good for something, or is it just nice to see?
They're nice to see, yes, and they will tell us more about the structure of the geometry very close to the black hole. So they are sort of they are characteristics of the very strong field geometry. And so seeing them in gravitational waves would be very, very interesting. And they are very hard to model also. You need to do a careful multi-scale analysis across the resonance and so on. They are pretty to see, and they are useful physically. And they are useful physically because of what I'm about to say next in the bottom of this slide, which shows a nice picture from the GRACE experiment. I like this picture because Cuba is in the center of it. You see, it's a satellite, a pair of satellites that was up there in orbit until 4 years ago, I think. And its purpose was to measure the gravitational field of the Earth very, very accurately. And so, the result of the experiments are shown here in some exaggeration. Places where the Earth is a bit more bulky, and places a bit more massive, and places where have some dips in it. And so the idea was to basically go around the Earth in an orbit with two satellites and exchange microwave radiation, measure the distance between them very, very carefully. And by monitoring small variation in the distance, you get a very accurate mapping of the gravitational field. And from this, you can deduce the mass distribution of the Earth. Now, I'm showing this to you here because EMRI is very much like that. You have a probe, a natural probe in that case, a star, a black hole, going around a big object, and via the gravitational waves that it sends you in this case, you get a map of the geometry around the big black hole. So in the case of GRACE, we were talking about geodesy, precision geodesy. In the case of EMRIS, we are talking about precision black hole geodesy. We have this thing here in the middle. And so that's why lots of people are interested in this. It allows you to test GR very, very accurately. The phase evolution of the EMRI is like a microscope into the precise geometry around the black hole. If you have deviations from GR from whatever reason, or you have a bit of accretion disk around it, a bit less interesting, then the EMRI waveform can look very, very different because the phase is sort of encapsulates and amplifies those little perturbations. Okay, so that's the big motivation. That's why lots of people are interested in this, and that motivates us, this big program to model those things in GR.
will you be able to disentangle these accretion disk astrophysical effects from real?
Very good open question. Yes, we think that it's not the leading order effect, but you know, as you measure things more and more accurately, this kind of astrophysical dirt will need to be taken into account. Yes.
I love the term.
Yes, we like the pure clean systems. If you want to learn about GR, that's what you like. If you like accretion disk, you want GR to be correct, and you want an accretion disk around the system. But the nice thing about the system is that it gives something to everyone. So yeah,
Leor, can I ask you something?
Yes, of course.
Are we going to be able to see if we get some small difference with the things that we expect, are we going to be able to say that this is because there is something more physically happening, or is it because our models are just not working in those in the very near to the black hole?
Yeah, so that's a very good question, and I'm willing to bet that when we see the first embryos coming from LISA, there will be lots of papers coming out offering different explanations, and there will be controversy and disputes. But that's how science progresses. And indeed, a lot of the effort that goes into data, understanding the data analysis problem, is really concerned with the question of how to distinguish between modeling error, perturbations from astrophysics, and perturbations from physics, from the theory itself. And it's not at all clear, and there are forms of perturbations that can look the same, even if there are different sources, and that's when things become interesting. We're hoping to see at least some very clean system without much astrophysical perturbations, that would allow us to learn about the physics, but again, we are left with sort of systematic type errors that come from modeling error. And these, again, we can control by just modeling it more and more accurately. So these are all open questions, and part of progress of science is trying to understand them once we finally get the signals. So yeah, it's not only accretion disk. We think we might be able to see systems where we have more than one embryo happening at the same time. So we have perturbations from a third object. Okay, so here's a statement of the mission, I think. Let me. Yeah, so all I described so far give us the mission description, mission statement. We want to calculate embryo orbits and the waveforms that they emit, and we want that to be phase accurate over a radiation reaction time scale, over a few years, the time during which LISA will be observing. We want the orbit to be in the strong field, so we can't use post-Newtonian approximation. It's not sufficient. We need the orbits to be sufficiently generic, and we know these things can be quite eccentric all the way to the end. The inclination with respect to the spin of the big black hole can be any. And we also want to allow spins on both of the black holes, as in the astrophysical problem. And we need to be quite accurate in the phase. And there's a little heuristic calculation of how accurate you want to be. So I'm looking at some orbital phase associated with some frequency of the orbit, and I'm sort of expanding it about an initial time. So the phase evolves with some frequency omega, but then there are corrections from radiation reaction. This is the back reaction from the emission of radiation, and that accumulates like the square of the time. That's why small corrections are magnified over time so magnificently, and allow you to get a good handle on the dynamics. But that also means that you need to model those deviations very accurately. So, for example, if you want to keep the phase error or the phase difference from such modifications to within 1 radian, say, over a period of radiation reaction time, you need to model those deviations to within 1 over the radiation reaction time, namely 2 order square to quadratic order in the mass ratio. That's because the radiation reaction timescale is like the inverse of the small mass ratio. The smaller the mass ratio, the more orbits you get, and the slower the evolution is. And so you need to know those back reaction terms up to 2nd order in the perturbation due to the small object. And this is hard. So it's not only solving a linearized version of the Einstein equation to get the field and back react with the field on the particle. You need to also calculate the 2nd order perturbation. So these are perturbations that come from putting the first perturbation as a source in the Einstein equation and solving for sort of the 2nd order perturbation. Those first order perturbation sort of ignite or excite higher order perturbations that are proportional to the mass squared, the small mass squared this time. And these two, back reaction from that too, needs to be taken into account. Since I'm running out of time, I'll just comment that we have both things under control now, and people have been ordered to calculate both of those perturbations up to 2nd order for astrophysical embryos. And the computers are cranking calculations now, and those waveforms are coming out. So I think very bad time planning on my behalf, but I just finished the first part of 4 parts of my planned talk. Let's see how I can conclude it in a meaningful way. Anyone wants to ask about this slide, first of all?
Come on. People, is it clear for everyone? I doubt it. I don't understand anything. Cuba people, talk. Well,
go ahead.
I'm just finding it a bit hard to imagine why it's so hard to calculate the expansion, but maybe it's just because I don't know the equations very well, I guess.
So let's see what it involves. You need to solve the you need to solve the Einstein equations to get the field, but it's enough to solve the linear version of it. So you just linearize in the small perturbation. You write the solution as a background, which is Schwarzschild or Kerr, plus perturbation. You write a linear version of the equations, and you solve it on a computer. And then you need to back react with this perturbation on the small object. But of course, if you just calculate the force, you'll get infinity, just like in electromagnetism. So you need to do something there, and there's this all infrastructure of regularization that goes into it, and that really But the bit where you need to solve the field equations, that's the hard bit, because there are issues of gauge freedom and lots of practicalities that go into it, and how to back react on the orbit and how to implement it over a very long time scale of the orbit. That requires a careful 2 timescale analysis, where you do an adiabatic expansion at leading order, and then you include higher order corrections that account for the slow evolution. And that requires a very careful step-by-step architecture. And it's all done numerically because you can't solve the field equations analytically.
Yes.
So, maybe, okay. I think we're going to start the next talk in 10 minutes, so maybe we should focus now on questions on what I said so far.
Cuba, everything clear? In stick, Solné, Joel, Fernando, somebody.
Maybe I can talk over this plot, like by way of concluding, just to tie to the beginning of my talk.
Oh yes.
So that's a plot that was presented last year by Martin van Ment and Harl Pfeiffer, collaboration between cell force people and numerical relativity people. That was an attempt to sort of better quantify this, give a bit more quantified picture like that, and try to identify where those borderlines sit. So what these two colleagues did was to marry results from full numerical relativity simulations of black holes, solving the full Einstein equations non-linearly, and calculations that come from cell force theory, so point particle around big black hole. In particular, Harald was running something like 60 simulations of black holes in full numerical relativity with mass ratios between 1 and 10, and then compare the phase evolution with what Martin van 't Midt was getting from evolving those orbits in perturbation theory with the first order cell force. And by comparing those two things, they were sort of trying to get an idea of where exactly and if they can be compared to each other in some domain on this space. And so let's look at this plot first that shows basically the phase, the accumulated phase as a function of the frequency along the orbit, as the frequency evolve along the orbit for a particular source. And so this sort of gray bluish is the numerical relativity evolution. It's broad because there's a large error there, numerical error. And the red line is the result from cell force. It's also broad, but you won't see the broadness because it's very accurate. These are linear equations, so it's much easier to get very high accuracy. You see how beautifully they sit on top of each other. And this is, I forgot what the mass ratio was for this one, but it's not big. It's a small mass ratio, and still the first order cell force is all does spectacularly well, almost all the way to the end of the inspiral. Now, by comparing these two things, you can sort of measure what would be the higher order cell force correction, the second order and the third order. And you can therefore create a map like this, which is, again, a quantitative version of what we have here, where here we have the numerical relativity results. We can't do anything beyond that at the moment. Simulation becomes extremely inaccurate above here. It takes too much time to run it with good accuracy. But we have a good agreement with what we call the small mass ratio approximation, the first order of it, in all of this range here, The result almost agree. And so if you sort of set an accuracy target, so how many radians of phase you allow yourself to lose, that gives you a sort of contour in this space. And you say that anything below this, if you run it just with the cell force simulation, you'll get it up to this accuracy over, I don't know, a year of inspiral or whatever they took here as a as a time, evolution time, some fiducial time. If you allow yourself less accuracy, an eighth of a radian, then you can do even better and go all the way up here with a quarter. So you see the small mass ratio approximation covers this entire region here. And it even blocks the small gap that exists today between numerical relativity and the post-Newtonian approximation that covers the rest of the space. So in a way, we think that we will be able to cover the entire space here by just combining this to the state of the art of what we have now between those two approximation schemes in available numerical relativity methods. There's a long way between this. There's a plot that I produced 20 years ago at the beginning of this effort, entirely just drawn by hand as a sketch, entirely heuristic. And I even guessed that this line is going to be sloped like that. And 20 years later, we are actually able to quantify it with calculation. And it looks remarkably similar, in my opinion.
Okay.
I have a question.
Mm-hmm.
So, from what I understand, these models are used primarily to study gravitational waves, right?
Yes.
So, does the since the size of the smaller black hole, since we're talking about extreme mass ratios, is very small, one would expect, I think, a large tidal deformation of the gravitational waves.
So that deformation of the small object, you mean?
Of the so could the tidal forces not emitted? Could the tidal forces due to the presence of the smaller black hole significantly affect the gravitational waves emitted by the system of those two black holes?
Tidal deformations of the big black hole, of the small black hole, both, you mean? There will be a deformation, that's true, yes. But for a black hole, they will be very small, and the calculation that we are doing take that into account, all the tidal deformations that of the black holes themselves. That is taken. That will be visible in the radiation, indeed. Yes.
Okay.
That's why we need the object, the small object, to be a compact object. If you're looking at the white dwarfs or normal main sequence star, they won't survive the inspiral because they will be torn apart by tidal forces and turn into diffuse clouds before they become interesting in the Lissa band. And that's why we need really the object, the small object, to be compact.
Okay, thank you.
Okay, easy math. Instec. Do you have questions, people? Kuba.
I do, but maybe
so.
If there's no other question, it's related to some question earlier and the comment you made about energy conservation in GR. It's a question I have since a long time, but I wasn't able to find the answer. Maybe you can give it. So if you have this two-body system, maybe any of the three, maybe we can separate in this plot, in the sketch here, and you go far enough away and you use this standard energy momentum tensor for gravitational waves in the like in this easy regime, let's say, to measure what comes out asymptotically at through a large sphere using this Isaac zone or something expression. Is energy then conserved? If
energy and ADM energy, and you can formulate a conservation law by looking at all the radiation, the total energy content of space-time as measured at spatial infinity, and you can balance that with the amount of energy that radiated to null infinity, calculate the Bondi mass, and the energy should be the difference between the ADM mass and the Bondi mass. And this applies to the two-body problem for Henry or for big black holes. There are such laws, yes, global laws.
But is that true even if the space-time is so perturbed near the black holes that maybe that geodesics process
relies only on asymptotic symmetries of the space-time? So these are things that are measured only at infinity, where space-time is almost flat. So that's
okay.
But the point for MRIs is that based on those alone, you can't model the system because you have important effect on the phase that are not radiative, like, for example, effects on the phase of the precession rate, that they don't encode themselves in the radiation rate. So you have to really measure local physics in order to understand how they affect the waveforms.
Yes.
The fact that it's all gauge dependent complicates things as well. So yes, you can use energy conservation to understand to model some features of the radiation, but not all of them.
Thank you.
You're welcome.
Okay, people, it's 28. I would like I would continue talking to Leor for like 3 more hours, but we have some time limitation here. So in STEC, in general, QA people, this is probably your last chance to ask Leor anything you want to ask.
Don't be so dramatic. You can email me and can have a chat.
Yes, but I mean during this talk.
Mhm.
Nothing? Yes, go ahead.
Yes. Hi, I have a question. Did you say that the small object cannot be a compact object like neutron stars?
Neutron stars is okay. So neutron stars will survive tidal forces all the way to the final plunge. So it's a good viable emery. But white dwarfs more, it's less clear. And anything larger than that is not going to be a good emery.
Okay. So this could not be used to constrain the properties of neutron stars or something like that?
Yeah, there is work on that. It's an interesting question. Yeah, so people think that actually by measuring the signal from white dwarfs before they get torn apart and during the process, we'll be able to learn about the question of states and so on, internal structure of neutron stars.
Okay, thank you. Yeah.
But for that, you have to go to black holes which are less massive, like 10 to the 4 and so.
Yeah.
Not 10 to the 6.
Yes, so yeah. You want to capture this early on, and they need to be sufficiently close to be visible in that case.
And we have a problem. We don't know whether these things exist. They probably exist, but we don't know that.
Yeah.
So, anyone else? Okay, then I'm going to. Okay, Salon Stick, we see you.
Somebody's raising their hand.
I think they're just greeting you and saying goodbye.
No. Bye.
Okay.
Am I going to go now?
Isimaf, are you fine? Okay. Giorgio, I think you can stop now.
No,